This is the 37th lecture and we talk about positive real functions today. Positive real function, if we denote it by f of s, is defined as a function f of s is PRF, a function f of s is positive real if and only if. Is a definition, very simple definition. Number 1, f of s is real for s real, it must be a real function. And number 2, the real part of f of s, should be non-negative for real part of s non-negative. Okay, f of s is real for s real and real part of f of s non-negative for real part of s non-negative. Real part of s non-negative means the right half plane, isn't that right? Including the j omega axis, that is, it is the closed right half plane. Therefore, what it means is that in the closed right half plane, f of s should also be in the closed right half of the f of s plane. Alright. In other words, we can view this in terms of mapping of one complex plane, that is S plane, to f of s plane. Do not be scared with the word mapping. What we simply mean is the following, that if we have an S plane sigma j omega and an f of s plane j imaginary part of f of s, and this is the real part of f of s, then what it means is that when s is real, this is the s plane and this is the f of s plane. When s is real, that is, when s is on the real axis, the pink line, f of s should also be real. Therefore, f of s must lie on this line. This is the mapping. That is, the S plane, this line maps into this line in the f of s plane. That is the first part of the definition. And the second part says that if real part of S is non-negative, which means that we take the closed right half S plane, when the real part of S is non-negative, then the real part of f of s should also be non-negative. In other words, the shaded area here maps onto the shaded area in the f of s plane. This is what is meant by mapping. Alright. It is an S to f of s mapping in such a manner that the real axis of the S plane maps onto the real axis of the f of s plane, and the right half of the S plane maps onto the right half of the f of s plane. That is the definition of a positive real function. A question, suppose I have a point, let us say here, let us say this point is sigma 0. What would be the possible location of on the f of s plane? Real axis, positive half. So, it would be somewhere here, let us say f of sigma 0. Alright. Another question, if you have understood the definition. Suppose I have a point here, let us say minus sigma 1. What would the corresponding f of minus sigma 1 be? Any point on the real axis. That is correct. So, it is a 1-to-1 mapping of the positive real axis of the S plane onto the positive real axis of the f of s plane. It does not mean that the negative real axis maps onto the negative real axis. No. Is the point clear?
So why not?
Why not? Because the definition only says that if real part of s is non-negative, then real part of f of s is non-negative. It does not say that if real part of s is negative, what will happen. It does not say. It only puts a constraint on the real part of s non-negative. If it is negative, then f of sigma 0 it has to be real, isn't that right? If S is on this point, then S is a real quantity and f of s has to be real, and therefore it must be somewhere on this line, but it does not specify where. It could be in the right half of the real axis or in the left half of the real axis. It could even be at the origin, it does not matter. Is the point clear? All that it says is that real part of S non-negative, that is the positive half of the real axis in the S plane, maps onto the positive half of the real axis in the f of s plane. Okay? These constraints must be kept in mind. They are simple mathematics, but the concepts are important, and if one loses sight of one small concept, one is able to make a Himalaya mistake. Okay? A mistake which is of the dimension of Himalayas. Now very simple examples. Suppose f of s is a constant, let us say k, where k is real and non-negative. K is real and non-negative. Obviously this function is PR. Why? Because when s is real, well, it's always real. It's always real. So s is real, it is also real. When real part of s is non-negative, k, it is a constant, that's always non-negative. So it is therefore a resistance, for example, f of s equal to a resistance or a conductance is a positive real function. A resistance is a positive real function, a conductance is also a positive real function. The impedance of an inductor, f of s equal to s times L, this is the impedance of an inductor. This is also positive real, because when s is real, it is real, and when real part of s is non-negative, the real part of f of s, after all, real part of f of s is equal to L times the real part of s, and therefore if this is non-negative, obviously this will also be non-negative. Therefore an inductor, the impedance of an inductor is also a positive real function. Okay. Let us take the impedance of a capacitor. Let us say f of s equal to 1 over s c. C is a real positive quantity. Alright. And you see that the first part of the definition is obviously met, that when s is real, this quantity is real. Now let us look at real part of f of s. This is equal to 1 over c, then real part of 1 over sigma plus j omega. Alright, and this is equal to 1 over c, real part of this is sigma squared plus omega squared, and the numerator you get sigma. And obviously if sigma is greater than equal to 0, so what is sigma? That is the real part of s. If sigma is greater than equal to 0, then obviously real part of f of s is greater than equal to 0. The sign depends on sigma, right? And therefore if sigma is non-negative, the whole quantity is non-negative. In other words, 1 by sc, the impedance of a capacitor, is also a positive real function. And in general, one can conclude that any network n which consists of passive elements like resistance, inductance and capacitance shall have an input impedance, a driving point impedance, which is positive real. And this is why our interest in positive real functions. The driving point functions of passive networks are positive real. Now we have not yet proved it. We have only said that of an inductance is positive real, impedance of a capacitor is positive real, impedance of a resistor is positive real. And after all, a transformer contains 3 inductances, and therefore the impedance should also be positive real. A combination of them which is contained in n, it appears to reason, it appears to intuition that it should also be positive real. But let us prove it. Let us make a rigorous proof and look at the proof. Very interesting proof. What we do is, let the input impedance be z of s. Okay? Let the input impedance be z of s, and let the current going in be capital I. Agreed? Then for sinusoidal excitation, that is s equal to j omega, for sinusoidal excitation, the power that is absorbed by the network, the power that goes into the network shall be magnitude I square divided by 2, capital I is the peak value, peak vector, magnitude I square divided by 2, this is the root mean squared current multiplied by no, the real part. It is the resistive part which absorbs power, the reactive part is reactive power. So, this will be the real part of Z of j omega, and since the network is passive, this should be greater than or equal to 0, which means that the real part of Z of j omega is greater than or equal to 0. Agreed? This is the first part of the first part of the proof. The second part, well, we have not proved anything, we have simply said that the real part on the j omega axis should be non-negative. Real part on the j omega axis should be non-negative. That does not mean that it should be non-negative over the whole right half plane. It does not mean that. Now, to prove that part, this is only a partial proof. To prove that part, let us modify capital N. Let us modify capital N to N prime such that what was an inductance in N is now, what was a pure inductance in N, let us add in N prime an inductance L in series with a resistance R. Okay? That is, N prime we make it into a more lossy network. Alright? In series with every inductance, we put a resistance such that the impedance of this element in N was SL, here it is SL plus R, and I can write this as L S plus R by L. Agreed? I can write this as L S plus alpha, let us say, and let the value of alpha be the same for each inductor. In other words, what I am saying is each inductor Li, where I can go from 0 to, where I can go from 1 to n, let us say, each inductor Li is augmented by a resistance Ri in such a manner that Ri by Li is a constant equal to alpha. We can do that. Every inductor that I find, I add a resistance alpha times Li. That is all that is mean. In series, I add a resistance. Alright. Similarly, every capacitor C in N is augmented, every capacitor, let us say Cj, is augmented in N prime by a shunt conductance Gj such that is, I make each capacitor lossy. Each capacitor in N, a loss is introduced in such a manner that Gj is equal to alpha times Cj. Alright? This alpha and this alpha is the same. We can do that. Okay? We take a box of resistors and just go on adding resistors across each capacitor in series with each inductor. We can do that. Now, then the capacitance, the admittance of this capacitor, which was SCj, now becomes Cj times S plus alpha. Is that clear? It becomes SCj plus Gj, SCj plus Gj, I take Cj common, therefore I get Cj times S plus alpha. Is that okay? Resistors in N we leave intact. That is, a resistor Rk in N goes as resistance Rk in N prime. Then what happens to the input impedance of N prime? What happens to the input impedance of N prime? You see, the only change that has happened is wherever S occurred in N, S should be replaced by S plus alpha, and therefore, is the point clear? Wherever S occurs, impedance of an inductor it is L times S plus alpha. In admittance of a capacitor, it is C times S plus alpha. Therefore,
What are we trying to do? I mean, what is our objective?
our objective will be clear in a moment. We are trying to derive another network N prime whose impedance now, instead of S, it shall be S plus alpha. This is what we wanted to derive. That is, from the given network N whose input impedance is Z of S, we want to derive a network whose input impedance is Z of S plus alpha. Let us call this as Z1 of S. Alright. Then by the same token as was applied to capital N, we must have real part of Z1 of j omega as greater than equal to 0. Is that right? For N, the real part on the j omega axis was greater than equal to 0. There is no reason why N prime should not also have the same property. All we have done is added a few resistors. We have not changed the character of the network, right? Therefore, real part of Z1 of j omega is greater than equal to 0, which means that the real part, that is, real part of Z of j omega plus alpha is greater than equal to 0. Clear? Because what is Z1 of S? It is Z of S plus alpha. Therefore, this means that real part of Z of j omega plus alpha is greater than equal to 0. I argue now that alpha was a purely arbitrary quantity. What was the constraint on alpha? That alpha should be non-negative. I cannot add a negative resistor. The resistor that I add in parallel with a capacitor or in series with an inductor, the only constraint is that alpha should be greater than equal to 0. If alpha is equal to 0, we get the original network. If alpha is non-zero, we get a derived network. And therefore, alpha is not a sacred notation. We could as well replace this by sigma, where the only qualification of sigma is that sigma should be real and non-negative. But what is sigma plus j omega? Isn't that precisely?
Yes.
Yes. Therefore, what we get from this derivation is that real part of Z of S should be greater than equal to 0. Is that clear? It's a very beautiful derivation, originally due to Kauer, Wilhelm Kauer, a German gentleman. Now, what does it mean? It means that Z of S is real for S real, and real part of Z of S is greater than equal to 0, and therefore Z of S, which is the driving point impedance of an arbitrary passive network. We have specified nothing. We only said it contains resistors, capacitors and inductors, nothing else. It could also contain transformers, because transformers are combinations of 3 inductors, and therefore we have proved that the driving point impedance of a passive network is positive real, and this is why we are interested in positive real functions. The connection between circuit theory and positive real function is through driving point impedance. Now, it takes a moment to justify that this property of positive realness also applies to a driving point admittance function. That is, yes.
Please explain the proof again.
Would you please explain the proof? Okay. What we did was, let's go back. What we did was, we took an arbitrary network N which contains resistors, inductors and capacitors, and we argued that the input impedance Z of S, its real part on the j omega axis must be positive. Why? Because the power absorbed by the network must be positive, must be non-negative. Okay? So, real part of Z of j omega is greater than equal to 0. From N, then we derive a network. From N, we derive a network, okay, by adding resistors in series with inductors and resistors in parallel with capacitors in such a manner that instead of Z of S, we get Z of S plus alpha. Okay? That is what we did here. In N prime, we added conductances in parallel with capacitors and resistor in series with inductors in such a manner that each SL now becomes L times S plus alpha and each SC becomes C times S plus alpha, and therefore all that changes in n prime is that S is replaced by S plus alpha.
If the network was passive.
Pardon me?
If the network was not passive.
If the network was not passive, then of course we cannot, this argument shall not be valid.
So,
If capital P is can be negative, then this argument is not valid. Yeah.
so while taking the value of P, sir, we take I square by 2 real Z j omega.
That's right.
So why can't we take directly Z S?
Why can I not? Oh, because the power in a sinusoidal excitation, the power is absorbed only in the resistive component. The reactive power is of no concern. The power, you see, the reactive power can be positive as well as negative, and there is an exchange between inductors and capacitors. Overall, the average reactive power is equal to 0, but the average power absorbed in a resistor will be non-negative. Okay, so it is on the passivity is on the basis of power absorbed by the network. All right, and that's why it was on the j omega axis.
So, but if you were to take a non-sinusoidal input, for instance,
A non-sinusoidal input can always be broken up into
sinusoidal.
sinusoidal input, and therefore it will be a sum of such terms. Okay. Any other question? So what we did was we argued that real part of z of j omega plus alpha is non-negative, and we argued that alpha was purely our choice. Alpha could be anything. Any non-negative value is admissible, and therefore we could replace it by sigma, where sigma is greater than equal to 0. Now if sigma is greater than equal to 0, then sigma plus j omega is the right plane, and therefore real part of it is S. It is S with sigma greater than equal to 0, it is the right half plane. Omega could be positive or negative, it does not matter, and therefore when S is in the right half plane, that is sigma greater than equal to 0, obviously the real part of z of S would be greater than equal to 0, which shows
We prove that real part of Z of S is 0 for all values of Z.
no, we did not say
All
that.
values of S.
Only the right half plane.
Only in the right half plane, not all values. You see, your sigma, your alpha was positive quantity. We could not add a negative resistor. Okay, so we prove that z of S, the driving point impedance of a passive network, is always positive real. Now we want to extend it to driving point admittance, and all that required is to prove a theorem that if f of S is PR, yes,
So we had this, we had to prove two things. F
Two
of S is
things.
real for S real.
okay.
So did we prove that? Z of S is real for S real.
Oh, we don't have to prove it, because Z of S after all is made up of SL, 1 by SC and R. Each of them are real for S real, and it will only be series parallel and multiple series parallel combinations. So all of these quantities would be real for S real. Okay, that is trivial, but this is not trivial. That real part of Z of S is non-negative is not a trivial proof. Any other question?
So why did we say that real part of z j omega is positive?
Why did we say that real part of Z1 j omega is good?
In the first case.
In the first case, because the power has to be non-negative. Okay, let's go back. This has to be non-negative, and this is a positive quantity, magnitude square divided by 2, and therefore this must be non-negative. Anything else? I appreciate these questions, because first time one meets synthesis does appear to be tough, but it's a very simple. Once you get over this fear of complex variables and this the functions are extremely simple functions, very nicely behaved, well behaved functions, nothing to be scared of. Okay, all right. As I said, z of S, the driving point impedance function, is positive real. We want to extend it to driving point admittance function, and all that is needed is to prove this theorem that if f of S is PR, then so is 1 by f of S. That is, if the impedance is PR, then the admittance is also PR, and it's extremely simple to prove. You see, if f of S is PR, then obviously 1 by f of S is real for S real. Agree? Because f of s is real for S real. And the other thing that you have to prove is real part of 1 by f of s. Okay? Suppose f of s is u plus jx. U is its real part and x is its imaginary part. Since it is a function of s, u is a function of sigma and omega. It is a two variable function. Similarly, x is a function of sigma and omega. You see, f of s, s is sigma plus j omega. I break this up, this complex function, into a real part and an imaginary part. The real part shall be a function of sigma and omega, imaginary part shall also be a function of sigma and omega. So, what is the real part? Real part of 1 over f of s? It is real part of 1 over u plus jx, which is equal to real part of u squared plus x squared, and in the numerator it is u. Pardon me?
U minus j.
We don't have to put the real.
Okay, u minus j. This is equal to u divided by u square plus x square. Alright, and obviously this is non-negative if u is non-negative. When is u non-negative? That is real part of s non-negative. Is that clear? Because by hypothesis f of s is PR. So, its real part is non-negative for real part of s non-negative. Okay. Therefore, this quantity is non-negative if u is non-negative, but u is non-negative in turn when sigma is non-negative. Therefore, we prove that the real part of this reciprocal function is non-negative for the right half plane, and therefore 1 by f of s is PR. And therefore, our theorem now states that all dpi's, and this I is now an immittance, IMMITTANC, it is impedance as well as admittance. All dpi's of passive networks are positive real. Okay, now the question of testing. But before we test, let us look at some useful properties. Properties of positive real functions. Some useful properties. One of them that I have seen is if f is PR, then so is 1 over f. This we have already proved. That is how we stated the theorem that all dpi's of passive networks are PR. Suppose f1 and f2 are PR. Then what can you say about f1 plus f2? That is also PR. The proof is trivial because real part of f is equal to real part f1 plus real part f2, and both of them are individually non-negative, so the sum is non-negative. What can you say about f1 minus f2? Not necessarily PR, okay, not necessarily, because the real part due to subtraction may become negative, not necessarily PR. Alright, next, poles and zeros of positive real functions. Where are they? Okay, cannot lie in the right half plane. Why not? Right half S plane. Why not? Poles and zeros of positive real functions cannot lie in the right half of the S plane. What is the reason? Pardon me? Which polynomial? It has something to do with the real part. It is a passive network. You see, all positive real functions, this is interchangeable, impedance, admittance or positive real functions. All driving point impedances are PRF. It can be shown that all PRFs can be realized by driving point impedance of passive networks. Now, if there is a pole in the right half plane, what does it mean? It means instability. That means the real part is no longer non-negative in the right half plane. What does instability mean? That the output can grow indefinitely without an input. That is the unstable condition. Alright? That is possible only when the network is able to generate power. Whereas a passive network, the power has always to be non-negative. So they cannot lie in the right half of the S plane.
So the condition of poles not lying in the right half plane is almost true for all the functions if they have to be stable.
No, that is not correct. Because for a transfer function, which is not a PR, not necessarily a PR, there can be zeros in the right half plane. For a transfer function, there can be, for example, I can have a function s minus 1 by s plus 1, which is an all pass function, as you know. The poles and zeros are in mirror image symmetry. Did we do this in the class? Yes. We have, okay. But it is not PR. If there is a positive real function, then the function as well as its reciprocal have to be PR. And therefore, we cannot have poles or zeros in the right hand plane. Okay. Number 4. Poles on the j omega axis. This is important, and we shall go slow on this. Poles on the j omega axis must be simple. Why simple? Because if they are multiple, then it leads to instability. Okay. Poles on the j omega axis must be simple. Now I am adding something to this for a positive real function with real positive residue. With real positive residue. Poles on the j omega axis must be simple with real positive residue. Okay. Now why is it so? Let us look at this. First we say why the residue should be real. But first let us see, if we have a function f of s with, let's say, two poles, one at j omega I and the other at minus j omega I. Well, complex poles must occur in conjugate pairs. Why?
Real.
Because the function is real for s real. Okay. So if j omega I is a pole, minus j omega I should also be a pole. And in f of s, if I expand in partial fractions, we shall have ki divided by s minus j omega I. That would be the partial fraction corresponding to j omega I, and for corresponding to minus j omega I, it should be s plus j omega I, then a residue which has to be complex conjugate of this residue. Why is it so? That is, this residue must be ki star. Why? Is the point clear? Okay, I could, let's write this as ki prime. Let's write this as ki prime. Now, if you add these two terms,
Which was real?
pardon me?
When you add them up.
When you add them up, the function must be real function, and it cannot be real unless ki prime is equal to ki star. Is this point clear? Therefore, and in addition it says that ki must be real. If it is real, I will tell you why it cannot be complex in a minute.
If Ki is real, then what is the use of Ki star?
If ki is real, then obviously both the residues should be same, identical. Let's assume for a moment that they are real. If they are real, then obviously if ki is equal to ki star equal to real, then obviously the sum of these two terms would be twice kis divided by s squared plus omega I squared, and this shows that ki, the residue, must be real, otherwise it cannot give rise to a real function. Okay, is that clear? Suppose, for argument's sake, that we do have a residue which is complex. Let us say we have K1 plus jk2 divided by S plus, let us say S minus j omega I. If I combine this with K1 minus jk2, will this sum be real?
Yes, sir.
Pardon me?
Yes, sir, it will be.
It will be real?
So we are adding a number with its conjugate. Because if,
Pardon me?
sir, K1 minus jk2 by S plus j omega I is conjugate of the first term. So it will be real.
Okay. In other words, I can have a residue like this, K1 plus jk2 divided by S minus j omega I plus K1 minus jk2 divided by S plus j
So
omega
it
I.
is conjugate of the first term.
Oh, so the sum shall be a real
Can
function.
be negative.
No, it cannot be.
It cannot be negative.
It cannot be negative.
It cannot be negative? Why not?
It can be.
It cannot be because the second term is conjugate of the first term.
Only given.
Both the numerator and denominator are the conjugate.
Okay. Same as the last. Now, the sum of these two terms, whether you take it in this form or in this form, the sum of these two terms shall be this. This Ki, can this be complex?
No, sir.
No, it cannot be complex. Okay. For a pair of poles on the j omega axis, Ki is the residue. Okay. Ki is the residue. That is, Ki is equal to the function. Let me write it in this next page. This point is not clear. Okay. If you add these two, you will get a real quantity, and the quantity must be of this form: 2kis divided by s squared plus omega I squared. Isn't that right? Where this Ki cannot be complex. It must be real. If it is complex, then the whole quantity will be complex. It cannot be a real function. And Ki, as you see, is given by f of s multiplied by s squared plus omega I squared divided by s twice s at s squared equal to minus omega I squared. No, this point is not clear. No.
If you add those two terms,
Yeah.
what you'll get is K1S minus 2K2 into omega I.
Okay.
So that can be negative depending on the value of K1 and K2.
K1 and K2 both.
All right. Let's clear this. S squared plus omega I squared. I get K1 plus jk2 s plus j omega I plus K1 minus jk2 s minus j omega I. Okay. This is equal to K1s K1s twice K1s
minus twice K2 omega I.
minus twice K2
Omega I.
omega I squared.
Only omega I.
No, only omega I divided by s squared plus omega I squared.
So
Now-
K1 S and omega K2 all are real. So this is real. So
K-
K1 and K2 both.
When s is real, the function is real. Okay, but the real part of this function can be negative. When s equal to j omega, for example, look at this. When s equal to j omega, this contributes to an imaginary part. This contributes to a real part, and depending on K2, it can be positive or negative.
So then property is not satisfied.
Pardon me? Then property is not satisfied. So this cannot be allowed. In other words, the residue K1
Should be positive.
should be positive and real. This is the proof. We did it in a slightly roundabout fashion, but
K1 must be positive and real.
K1 must be positive and real. It cannot
Is
be.
it sufficient?
No, it is not sufficient. I am coming to that.
So what do you mean by residue?
Oh, this is what I was going to decide. This is what I was going to. You see, if f of s is, let's say, of this form, some numerator divided by s squared plus omega naught squared multiplied by, let's say, some polynomial d of s, then obviously we have a pair of poles on the j omega axis at plus minus j omega naught. Then the residue k naught at this pole, at either of the two poles, is defined as s squared plus omega naught squared multiplied by f of s divided by twice s at s squared equal to minus omega naught squared, which simply means that what we have done is that we have expanded f of s in partial fraction. We have expanded this in k0 by s plus j omega naught plus k0 divided by s minus j omega naught plus other terms. That is what k0 is. K0 is called the residue at the pole at plus minus j omega naught, and this residue must be real and positive. Why positive? You are convinced about the realness of it. Okay. Why positive? Suppose k0 is negative. Suppose k0 is negative. After all, the term that comes is twice k0s divided by s squared plus omega naught squared.
Then it doesn't remain a PRF anymore, because if k0 is negative, real s greater than 0. No matter what the whole term, real fs will become less than 0.
No, I didn't follow.
So if k0 is less than 0,
Yeah.
it means that for real s greater than 0, this whole product will become less than 0.
Real plus
Real product.
That is correct. The real part condition shall be violated, and therefore k0 must be real and positive. Alright. This point must soak in that if a positive real function, Tanvi? Oh, what is the real part of this? The real part in the numerator shall have twice k0 multiplied by sigma, and if k0 is negative, obviously sigma non-negative will make the real part negative.
Yes.
Okay, and therefore k0 must be real and positive. The sum of this discussion, sum and substance of the discussion, is that if a positive real function has a pole on the j omega axis, this pole cannot take any liberty, it must be constrained. The constraint is that the pole must be simple, number one, and the residue at this pole must be real and positive. Okay? If f of s, if a positive real function has a pole on the j omega axis, it must be simple and the residue there must be real and positive. Next, suppose f of s, fifth property, yes. Suppose f of s, now we bring in a further restriction that our positive real functions that we shall deal with are all rational. If you have a finite number of resistors, capacitors and inductors, obviously the impedance function or admittance function or any function, any network function has to be rational. What is a rational function?
T by Q.
What is PS and what is QS? Both are. What is a polynomial?
Any expression of the form
The
A
highest.
extends.
Polynomial?
Positive integer.
That's it. A polynomial, you are not saying the key thing.
Positive real.
The highest power has coefficient 1.
Positive real integer.
What is the number of terms in the polynomial?
Finite.
So it is a finite series. That is the essential part of the definition. It's a finite series containing positive integral powers of the variable. Okay. Now the question is, what can be the difference in degree between P and Q? We use the simple notation. Degree of P is simply written as P and the temperature degree. Okay. What can be the difference between the degrees of P and Q? The difference, so I don't have to put this sign. This is equal to, what are the possible values? Can it be 0? Can the degrees be equal? Yes. If the degrees are equal, then what is the behavior at infinity? A constant. Okay. Now can the degrees differ by 1? Yes. Then what is the behavior at infinity? A pole or A 0. Now what is a pole of f of s is a 0 of 1 over f of s, and what is a 0 of f of s is a pole of 1 over f of s. Therefore, a difference in degree of 1 is permitted. What about 2? No, because then we shall have multiple poles or zeros at infinity. So the degree difference between P and Q can be at the most 1, 0 or 1. Alright. What does this mean? This means that the highest powers, if I write this as s to the n plus etc. and s to the m k, then it means that the highest powers can differ only by 0 or 1. Alright. They cannot differ by more than 1. Now m can be greater than n or n can be greater than m, it does not matter. What can you say about the lowest powers? Suppose the constant term here is a0 and there is no constant term here. Suppose the final term is b1s. Is this permitted? Is it permitted to have b0 equal to 0?
Yes.
Constant. Suppose b0 is 0, then we shall have a pole at the origin. If a0 is 0
0.
and b0 is not 0,
Then it is
then there is a 0 at the origin. Can we have in the denominator b0 and b? That is right. What does this mean? That the lowest powers in numerator and denominator cannot differ by more than 1. Okay. So this is the sixth property. Lowest powers in numerator and denominator cannot differ by more than unity. Alright. So but if I combine the two, I can say that if the function is positive real, these are all necessary conditions, they are not sufficient. Isn't that right? Even if these properties are true, the function may not be positive real, because we have said nothing about the real part yet. Alright. Therefore these are all necessary conditions, not sufficient. But we can say that the lowest powers as well as the highest powers cannot differ by more than 1. For example, pardon me? Why it is so? Okay. Let us take some examples. Suppose I have s squared plus s plus 1 divided by, let us say, 3s, s squared plus 3s. Okay. Then obviously at s equal to 0 the function is a pole. On the other hand, if 3s is also absent, then also it has a pole, double pole, and therefore the lowest powers cannot differ by more than 1. Is the point clear?
Yes.
Let us take some examples.
Sir, why should poles on geometry axis be simple?
Well, that we have already elaborated. If it is not, okay, what does a pole on the j omega axis cause in the time domain? Time domain, it is either a sine function or a cosine function. If there are multiple poles, for example pole of double order, then this is multiplied by t.
So
Which
definition of PRF.
from definition of PRF, well, instability means that the real part condition shall be violated. Instability means that the real, that is the power, can be negative. Okay? Alright. Now let us take a few examples. Suppose I take s plus 1 divided by s squared minus s plus 1. Can this be PR? This can be PR. Now tricky question. You said the denominator there is a negative sign. What does it mean? There must be poles in the right up plane. That means this polynomial is not Hurwitz. Okay? That is the point that I wanted to bring. If I write a network function as P of s by Q of s, one of the necessary properties is that both P and Q must be Hurwitz. Okay? Must be Hurwitz. Alright? Suppose I have s cubed plus s squared plus 1 divided by, let us say, 5s cubed plus 6s squared plus twice s plus 2. Numerator is not a Harris polynomial because there is a missing term. Okay, we will have more fun next time on examples and go into more details of positive real functions.